A man's heart stops. Clinically, he is dead. No pulse, no breathing. The monitors flatline. And then 47 seconds later, the doctors bring him back. And he says something strange. He says, "I saw a light. Not a flashlight, not a lamp." He says it was a white light, brighter than anything he had ever seen. And it was at the end of a long, dark tunnel. And he was moving toward it. And he felt the most extraordinary peace he had ever known. His wife is standing there crying. The nurse is writing on a chart. The doctor is checking vital signs. And the man is lying there perfectly calm. And he says, "I have never been so sure of anything in my life. There was a light, and it was real." Now you might say that is a spiritual experience. You might say that is the soul leaving the body. You might say it is heaven or God or the great beyond. And I have no quarrel with people who believe those things. But I am a physicist. And as a physicist, I want to ask a different kind of question. I want to ask, can physics explain what this man saw? Can the laws of nature, the ones that govern light and electricity and the behavior of atoms, account for every single detail of this experience? My answer is going to surprise you, because the answer is yes. Every piece of it. The tunnel, the white light, the feeling of peace, the sensation of floating. All of it has a physical explanation, and the explanation is not vague hand-waving. It is precise, it is testable, and it begins with one of the most remarkable machines in the known universe, the human eye. So let us start there. Let us start with how you see anything at all. And I mean really how down at the level of single atoms and single particles of light. Right now, as you look at the world around you, photons are streaming into your eyes. Photons, little packets of electromagnetic energy. They come from the sun or from a light bulb, or they bounce off the face of a friend, and they enter through your pupil, pass through a lens, and land on a thin sheet of tissue at the back of your eyeball called the retina. And on that retina, packed together like sardines in a can, are about 130 million photoreceptor cells. 130 million. That is more cells in one retina than there are people in Japan. Rods and cones. The rods are the ones that work in dim light, and the cones handle color. That is the apparatus. But the magic, the real magic, is in the chemistry. And honestly, the more I think about this chemistry, the more it astonishes me. Each rod cell contains a molecule called rhodopsin. Rhodopsin is a protein, a big complicated folded-up chain of amino acids. And sitting inside that protein, cradled in a little pocket between 7 helical columns, is a much smaller molecule called retinal. Retinal is a form of vitamin A, and this retinal molecule sits inside the rhodopsin protein in a very specific shape. It is bent, kinked. The chemists call it 11-cis retinal because there is a kink at the 11th carbon bond in the chain. Think of it like a crooked finger. When a single photon, one particle of light, hits this molecule, something astonishing happens. The photon's energy is absorbed by the retinal, and that energy causes the kink to snap straight. The 11-cis retinal flips to all trans-retinal. The crooked finger straightens, and this happens faster than almost anything else in biology. 200 femtoseconds, let me tell you how fast that is. A femtosecond is 1/millionth of 1/billionth of a second. 200 femtoseconds means the reaction is over before a beam of light could travel the width of a human hair. It is one of the fastest chemical reactions ever measured in any living system, and arguably one of the fastest measured anywhere. Think about what is happening at that speed. The atoms in the retinal molecule do not even have time to bump around from thermal motion. The surrounding water molecules have not moved. The protein has not flexed. Nothing has happened except this one precise quantum mechanical event. A photon has deposited its energy, and the molecular shape has changed. It is like a lock clicking open. One photon, one click, and the efficiency is extraordinary. About 67% of the photons that are absorbed successfully trigger the isomerization. 67% quantum efficiency. For comparison, the best solar panels humans have ever built achieve maybe 25% efficiency in converting photon energy. Your rod cells blow them away, but it does not stop there, because a single molecular shape change is a tiny event, a few atoms shifting by a few angstroms. How does that become a signal that your brain can read? The answer is amplification. Massive amplification. The straightened retinal pushes against the rhodopsin protein, which changes its own shape. The shape-changed rhodopsin activates another molecule called transducin. One rhodopsin can activate about 500 molecules of transducin. Each transducin activates an enzyme called phosphodiesterase. Each phosphodiesterase molecule chews through about 1,000 molecules of cyclic GMP per second. The cyclic GMP is what keeps ion channels open. As it gets destroyed, channels close, and the closing of those channels changes the electrical charge across the cell membrane. So let us count. One photon activates one rhodopsin. One rhodopsin activates 500 transdopsins. 500 transdopsins activate 500 phosphodiesterases. Each one destroys 1,000 cyclic GMP molecules per second. That is 500,000 molecules of cyclic GMP destroyed per second, which closes enough ion channels to block the flow of roughly 1 million sodium ions. One photon, one molecule, 1 million ions. That is a gain of 1 million. Your retina takes a signal the size of a whisper and amplifies it to a shout. And this whole cascade from photon absorption to electrical signal takes about 1/50th of a second. You absorb a photon, and 50 milliseconds later there is a measurable voltage change in the rod cell. It is engineering of the highest order, and it was engineered by nobody. It was built by evolution, by billions of years of trial and error, atom by atom, molecule by molecule, each slight improvement conferring a slightly better ability to detect light, to see predators, to find food, to survive. But there is a problem that evolution had to solve, and the solution is crucial to our investigation. If your detector is this sensitive, if one photon can trigger a cascade of 1 million ions, how do you prevent false alarms? Because molecules jiggle, they vibrate. At body temperature, thermal energy is constantly shaking every bond in every molecule. What stops the retinal from spontaneously flipping shape just from the random thermal jostling of the atoms around it, with no photon involved at all? The answer is remarkable. It almost never happens. The rhodopsin molecule is so precisely shaped by evolution that the retinal is held in its kinked position by a cage of protein interactions, suppressing thermal false alarms to an astonishing degree. A single rhodopsin molecule thermally isomerizes accidentally, on average once every 420 years. Per molecule, you have about 100 million rhodopsin molecules per rod cell, so the math works out to a very occasional phantom event, maybe a few per minute across all your rods, and you can actually perceive them. If you sit in a perfectly dark room for long enough and pay close attention, you will see tiny sparkles of light that are not light at all. They are thermal accidents at the molecular scale. The random motion of atoms occasionally kicking a single rhodopsin hard enough to flip it, which triggers the whole cascade, producing a signal your brain cannot distinguish from a real photon. This is critical for our story. It tells you something profound. The visual system can produce the experience of light without any light entering the eye. The machinery can be triggered from within. Under normal circumstances, this internal triggering is vanishingly rare, because 420 years is a very long time for one molecule to wait. But under abnormal circumstances, when the chemistry changes, when oxygen vanishes and cells start behaving erratically, the internal generation of signals can become enormous. That is the first hint, the first real clue that the white light people see near death might not be coming from outside at all. It might be the system generating its own signal, flooding itself with phantom light. Let me hold that thought. I want to show you another clue before we put it all together. Fighter pilots. When a jet fighter makes a sharp turn, the centripetal acceleration can push 8 or 9 times the force of gravity onto the pilot's body. At those forces, blood drains out of the head. The brain starts losing its supply. And the pilots, right before they lose consciousness, report something very specific. They report tunnel vision. The periphery of their visual field closes in from the edges, like the iris of a camera shutting down, until all they can see is a shrinking circle of light at the center. Then, if the forces persist, even that circle goes dark, and they black out. The military calls this G-lock, gravity-induced loss of consciousness. And here is the part that should make you sit up. The pilots who hover at the edge, who experience partial loss of consciousness without fully blacking out, describe an experience that reads like a near-death report. The tunnel, the light at the center, sometimes a feeling of deep peace, sometimes vivid, dreamlike episodes. Some pilots have described conversations with people who were not there, and they say the experience felt more real than ordinary life, not less. Why does this happen? Because the retina, like the brain, needs blood. When blood pressure drops, the retinal vessels constrict, and they constrict from the periphery inward because the peripheral retina is served by the thinnest, most distal branches of the retinal artery, with the lowest pressure and the highest resistance. The central retina, fed by a richer vascular supply near the optic disc, holds out the longest. So as the blood drains away, peripheral vision fails first, then progressively closer to center, creating a shrinking circle of sight surrounded by blackness, a tunnel with a light at the end. This is retinal ischemia doing exactly what the physics of blood flow predicts. No mysticism, no metaphysics, hydraulics, and the phenomenology is almost identical to what dying patients describe. That is an enormously strong clue because it tells us we can reproduce the tunnel experience without anyone being close to death. All you need is to cut the blood supply to the retina. The geometry of the vascular system does the rest. So now we have two independent mechanisms that can produce a tunnel and a bright light without any external source of illumination. First, retinal ischemia, which collapses peripheral vision inward as blood supply fails from the edges. Second, as I will show you shortly, cortical disinhibition, which fires up the center of the brain's visual map through a completely different pathway. During the dying process, both probably occur simultaneously, and they both point to the same conclusion: the light is coming from inside. I have told you all of this, and in considerable detail, because I need you to appreciate something fundamental. Your visual system is not a camera. It is not passively recording the world. It is an active, screaming, roaring electrochemical machine, powered by oxygen and glucose, consuming enormous amounts of energy every second of every day. Those rod cells, those cone cells, the bipolar cells, the ganglion cells, the optic nerve fibers, the entire processing chain from retina to brain, all of it requires a constant, rich supply of oxygenated blood. Cut the oxygen and the machine starts to fail. Not all at once, not uniformly, but in a very specific, very predictable pattern that turns out to be the key to everything we are investigating today. So now let us follow the clue to the next stage. What happens to this beautiful machine when you are dying? When the heart stops, blood stops flowing. Within seconds, the oxygen level in the brain begins to drop. The brain is a glutton for oxygen. It weighs about 2% of your body mass, but it consumes 20% of your total oxygen supply. So when the supply is cut, the brain notices immediately. But not all parts of the brain are equally sensitive to the drop. Some neurons are hungrier than others. Some circuits fail before the rest. And this is where the investigation gets very interesting, because we are about to discover a pattern. In the visual cortex, which is the part of the brain at the very back of your head that processes everything you see, there are two main types of cells: excitatory neurons and inhibitory neurons. The excitatory neurons are the workhorse cells that fire when they detect a feature, an edge, a contrast, a motion. The inhibitory neurons do the opposite. They prevent excitatory neurons from firing when they should not. They are the governors, the brakes, the referees. Without inhibition, every excitatory neuron would fire at every provocation, and the result would be meaningless noise. Here is the critical fact: inhibitory interneurons are among the most metabolically demanding cells in the entire brain. They fire at incredibly high rates, sometimes hundreds of times per second, and maintaining that rapid fire requires enormous amounts of energy. They burn through oxygen and glucose faster than almost any other cell type. They are, in a sense, the hardest working cells in the cortex. So when the oxygen drops, which cells fail first? The hardest working ones. The inhibitors. The referees walk off the field. And what happens when the referees leave? The game collapses into anarchy. Every player does whatever they want. In neural terms, the excitatory cells, which still have some residual energy, begin firing spontaneously, not because they have received a signal from the eyes, not because there is any light entering the system. They fire because nothing is stopping them anymore. Random, spontaneous, uncontrolled electrical activity spreading through the visual cortex. Now, if all you knew was that neurons were firing randomly, you might expect the result to be a blur, a uniform glow, static, snow on a television screen. But that is not what happens. And to understand why, I need to tell you about a map. Your visual cortex is organized, beautifully organized. It contains a map of your visual field, and this map is one of the most precise topographic structures in the entire nervous system. The neuroscientists call it a retinotopic map. Every point in your visual field, from the center of your gaze to the far edges of your peripheral vision, corresponds to a specific location on the surface of your visual cortex. If I could lay your visual cortex flat, which you cannot do because it is folded, but if I could and I touched a spot with an electrode, you would see a flash of light at the corresponding position in your visual field. The mapping is exact, but, and this is the clue we have been looking for, the map is not proportional. It is wildly distorted, grotesquely distorted. The center of your vision, the tiny spot right where you are looking at this very moment, gets an enormous amount of cortical real estate, an absurd amount. About 25% of the entire primary visual cortex, a region roughly the size of a credit card, is devoted to processing just the central 2.5 degrees of your visual angle. 2.5 degrees. That is about the width of your thumb held at arm's length. Meanwhile, the vast sweep of your peripheral vision, which covers more than 170 additional degrees, gets squeezed into the remaining 75%. Put another way, fully half of your visual cortex processes only the central 10 degrees of vision. The other 170 degrees share the other half. The center is represented by maybe 50 times more neurons per degree of visual angle than the far periphery. Neuroscientists call this cortical magnification. The fovea, the central point of sharpest vision, is magnified on the cortical surface. It gets more neurons, more connections, more processing power per unit of visual space. And this makes perfect biological sense. The center of your gaze is where you need the finest resolution. It is where you read, where you recognize faces, where you thread a needle, or aim a rifle, or pick a berry from a thorny bush. Evolution packed neurons into that region with lavish generosity and left the periphery comparatively sparse. Let me give you an analogy to make this concrete. Imagine a country where the capital city occupies 1% of the land area but contains 50% of the population. Every other city and town and village in the entire rest of the country shares the other 50%. If you drop confetti randomly from an airplane across the entire country evenly, 1 piece per square mile, then the capital would accumulate vastly more confetti per unit of perceived importance than anywhere else, simply because it has more people per square mile to notice the confetti falling. Not because the airplane favored the capital, because the population density is biased. That is cortical magnification. The visual cortex is the country. The neurons are the population. The center of vision is the capital city, and the random neural firing during oxygen deprivation is the confetti. It falls evenly across the cortex, but because the cortical population density for center of gaze is so much higher than for the periphery, the perceived brightness is concentrated at the center. Under normal conditions, this distortion is invisible to you. Your brain compensates. The world looks even, continuous, seamless. But under abnormal conditions, the distortion reveals itself. And dying is about as abnormal as conditions get. So, let us put the clues together. Inhibitory neurons fail. Excitatory neurons fire randomly. The visual cortex map is not proportional, but massively biased toward the center. What does random firing look like through this distorted lens? If every neuron has roughly the same probability of firing spontaneously, and the center of the visual field is represented by vastly more neurons than the periphery, then random firing produces a vastly stronger signal at the center than at the edges. Not because anything special is happening at the center, just because there are more dice being rolled there. More neurons, more chances to fire, more perceived brightness. You would perceive a concentrated brightness at the center of your visual field, surrounded by relative darkness at the periphery, a bright core fading to shadow at the edges. You would see a light at the end of a tunnel. That is not mysticism, that is not metaphor, that is geometry. The geometry of the retinotopic map, combined with the statistics of random neural firing, combined with the differential vulnerability of inhibitory neurons to oxygen deprivation. 3 facts from physics and neuroscience, stacked together, and out pops the single most commonly reported feature of the near-death experience. And I should point out something else. The light is described as white, and not red, not blue, not green. White. Why? Because white light in terms of color perception is what you see when all 3 types of cone cells, or all regions of the color processing cortex, are stimulated simultaneously and roughly equally. When the disinhibition fires up the visual cortex randomly, it does not preferentially activate color-specific neurons. It activates everything. All the color channels fire at once. and the brain interprets simultaneous activation of all color channels as white. It is the same reason a television screen showing red, green, and blue pixels all at maximum intensity looks white. It is the same reason sunlight, which contains all visible wavelengths, appears white. Random broad-spectrum neural firing produces a broad-spectrum percept. White. And here is a fact that should give any honest investigator pause. The tunnel and light experience is reported across cultures. About 10 to 20% of people who survive cardiac arrest report some form of near-death experience. That number comes from multiple prospective studies, including a landmark Dutch study that followed 344 cardiac arrest survivors. 18% described an experience, and the experiences share a common core. It appears in accounts from the United States, from India, from China, from sub-Saharan Africa, from indigenous Australian communities. Children report it, elderly patients report it, people with no prior knowledge of near-death experiences report it. The details vary, certainly, the cultural interpretations differ, but the core phenomenology, the tunnel, the bright light, the feeling of peace is strikingly consistent. If this were a purely cultural phenomenon, a product of expectation and religious belief, you would expect enormous variation. Christians would see heaven. Hindus would see the cycle of rebirth. Atheists would see nothing. But that is not what happens. The basic experience transcends belief, which strongly suggests it is rooted in biology, not theology. The hardware is the same in every human brain. The cortical magnification is the same. The retinal blood supply fails the same way. The inhibitory neurons are equally vulnerable in a Tibetan monk and a Texas rancher. So the hallucination, if we can call it that, is the same. But we can go further. A researcher named Susan Blackmore built a mathematical model of exactly this process. She used the known equations for cortical magnification, the known relationship between neuron density and eccentricity in the visual field, and the known behavior of excitatory neurons when inhibition is removed. She ran the math, and what came out was not just a vague glow, it was a specific dynamic pattern. As disinhibition spreads through the cortex, the random firing increases. The bright spot at the center grows. It expands outward. From the perspective of the person experiencing it, the bright region appears to be approaching, or equivalently, the person appears to be moving through the tunnel toward the light. The expansion follows a specific mathematical curve determined by the logarithmic mapping function of the retinotopic representation. The model predicts not just the tunnel, not just the light. It predicts the motion through the tunnel. All from one set of equations and one physical principle, the geometry of the cortical map under conditions of failing inhibition. Nobody had to invent a soul to explain it. Nobody had to invoke another dimension. The answer was sitting in the map all along. Let me stop here for a moment and let that sink in, because I find it genuinely extraordinary. The cortical magnification that gives you sharp central vision during life, the same magnification that lets you read a book, recognize your mother's face from across a crowded room, spot a hawk against a bright sky, that same architecture, that same geometric bias, is the thing that gives you a tunnel of light during death. The hardware serves two purposes, one for living, one for dying, and nobody designed the second one. It is a free gift from the geometry. Now I know there is a voice in your head saying, all right, Feynman, fine. Fine. You have explained the tunnel and the light. Very clever. But what about the rest? What about the overwhelming feeling of peace? What about the floating? What about people seeing their dead relatives? Does physics explain all of that too? Let us see. The feeling of peace. When your body is under extreme stress, when the heart is failing, when oxygen is plummeting, your brain does something it has been preparing to do your entire life. It releases a cocktail of endogenous opioids, endorphins. These are molecules manufactured by your own neurons, and they